It's great to be with all of you. I can look through the participants and see many friends and colleagues. So it's wonderful to be with all of you, and especially with the students. Just like Charles Dickens, this is a tale of two epidemics. And in the opening line, it was the worst of times and the best of times. He sort of flipped that, or I flipped it. The worst of times is kind of obvious. The best of times is the use of science to solve a lot of the problems that we're encountering, both with HIV and with COVID. So I'm going to go through starting off with HIV. And before I get started, I have a couple of grants that are winding down from Gilead and ViiV, and that's all my conflicts. So this is HIV. It's a virus, obviously. It was discovered in 1993. And I think the important thing to note is that AIDS as an entity was described in June of 81. So it was well over 2 years since the first cases of AIDS were defined, 2 years that they actually even defined the etiologic agent. And so it was a mystery for many years. And you contrast that with COVID. And COVID was the first defined towards December of 2019. And by early 2020, the virus was well characterized, and the sequence was released on January 10th, and the candidate vaccines were created, at least the Moderna one was created at the National Vaccine Research Institute 2 days later. So that's part of the tale of the two epidemics, is that whatever happened in HIV is happening at warp speed with COVID, and it's something that we should celebrate. The other thesis of the talk today is that we're building all of our responses to COVID on the shoulders of epidemics that came before, and probably most prominent of which is the HIV epidemic and the science that evolved. So I'm going to spend the first part of the talk talking about a little bit about the HIV science and how it relates, and then segue over to where we are with COVID and where we might be going in the future. And along the way, I'll talk about a resource that's available to all of you called Scenics, and I'll get to that in just a little bit. So the first thing I want to talk about, I know there's a big game tonight and you may be pulling for Georgia, which is fine. I think it's great that the two top teams are playing tonight, and I don't have too much of a dog in the fight. But I do like the way that Nick Saban coaches, because it's not about individuals. It's not about a group. It's about a team. And team science is really what it's all about, in my opinion. And what I mean by that is that you have a team of people who are focused on one singular objective or question, and you bring those people together based on their talent and their ability to contribute. As that question is solved or moves on, then the team, it's okay for the team to disband and go in other directions, as opposed to a group, which is often a study group where the people are put together in a room and they come up with an agenda, but sometimes the group itself takes on more of the meaning of what the effort is. And sometimes the objective of the group is mostly just to hang together and keep going, whereas a team is focused on a specific question. And to me, the most impactful science occurs when you bring a group of people together with diverse expertise, and you focus them on a particular question, they solve it, and then they move on. And sometimes they can come back together. That's not a problem. But that's one thing I've learned over the 4 decades of my career, is working on a team is very important to answer questions. I'm going to give you a couple of examples of that in HIV, and then also talk about COVID along the way. So this is the first team I worked with on HIV. It was in 1987 when I was in the lab of Beatrice Hahn and George Shaw. And what we discovered was the quasi-species nature of HIV. And not to belabor the point, but what you can see is that when you do a southern blot, there's definitely more than one type of variant present in the bloodstream of a single person. And what we went on to show was that a person gets infected with a single type of HIV, and then based on immune system pressure, that virus mutates and changes to avoid the immunologic pressure And you get this cat and mouse game of the immune system responding, but then the virus mutating. And we know that the virus replicates at a very high rate, and it's just a survival of the fittest. As a new, more fit variant comes up in that patient's bloodstream, it becomes a dominant variant. And I don't have to spend a whole lot of time describing the similarities to the emergence of variants with COVID, but the difference here is that the emergence of variants as done in this paper was really all about an individual and its response. And with the emergence of variants in COVID, it's more that the individual in that case is the population. And the virus replicates at high rates going person to person. And then while inside that person, a accident happens in translation and transcription such that a variant can emerge and be more fit. And Darwin was right in the 1840s and 1850s. Survival of the fittest is indeed how biology works. And this is a good example. We later learned that HIV replicates at 1 to 10 billion viral particles a day. The SARS-CoV-2 virus is similar in terms of its speed and ability to replicate. The difference is that HIV makes a mistake out of its 9,000 base pairs, at least one mistake each replication cycle. So lots of variants being produced. SARS-CoV-2 is a 30 kilobase virus that makes mistakes, but it has something that HIV doesn't. It has spell check. It has an enzyme that looks at fidelity of transcription specifically for that. The human body has a lot of that. As we have our cells replicate, there's a lot of fidelity because of those types of spell check enzymes. HIV doesn't have it. So a lot more individual variants with HIV, most of which are not viable. But the ones that are viable can escape immune pressure, do that because it's just basically Darwinism. Then, as Sadiq mentioned, we stumbled onto viral load through a collaboration, a team of people, a couple of whom I've never worked with before and only worked with a couple times since. But this is a group that was in Gene Labs in Redwood City, California, Mike Piatek and Jeff Lifson. And they called one day and said, hey, we got this way to quantify PCR. And we said, great. And I had the repository and I had a database. We started that on day one at the UAB 1917 clinic, and as part of the clinical core of the Center for AIDS Research, we were one of the first 7 funded NIH CFARs, and we've been continuously funded since 1988. But a core part of what we had was a database and a specimen repository, and that was the foundation. I remember vividly writing the clinical core on that first application. And one of the critiques that came back, it got funded, but one of the criticisms was, okay, you have this database and the specimen repository, what's your hypothesis? And I kind of went, gosh, I guess the hypothesis is one day these specimens and data will be valuable. So that turned out to really be the case, because when Jeff Lifson called me, I had a lot of patients well characterized, and I picked about 80 of them with different stages of disease and ended up showing this in essence, which was the virus, as far as P24 antigen, think antigen test with COVID, would go away in most people after the acute seroconversion syndrome. Sometimes it came back in these closed triangles. But what we saw with the viral load was that it was present throughout. It was present all throughout this time. That's these triangles here. And that told us for the first time, explained the mystery of how HIV progressed, that we knew that viral replication was going on continuously as opposed to going latent, which was the thinking at the time pre-1992. And this was a major step forward because it told us a lot about the pathogenesis. We've used that knowledge of HIV and its ongoing replication in COVID because it tells us not only what's happening inside a patient during those first 7 days of infection with ongoing replication, but it also tells us a lot about transmission and transmissibility and how the immune response, you can see here with acute infection, the immune response drives down by a couple of orders of magnitude. This is a log scale. The same thing happens with SARS-CoV-2, except in that case, it eliminates replication completely, the immune system response. We later went on to develop specific drugs in collaboration, a team, in this case with people from Merck, Emilio Amini and Oscar Laskin. And this is a 6-week study, believe it or not, where we showed that you can give a single drug, in this case, L697-661, which we now know as efavirenz. And you can see that, I guess this last bottom panel shows it. In 1 week, the viral load went down dramatically, stayed down, and then came rebounding back at week 5. And that was coincident with the development of resistance. And so it taught us not to use monotherapy, especially with non-nucleoside agents, but we don't use monotherapy at all anymore with HIV. In the case of COVID, we are using therapies, but because the immune system response kicks in so early and is so effective at eliminating the virus, what we're doing there is we're just giving the immune system a leg up, be it with monoclonal antibody or these new drugs, as Paxlovid and molnupiravir. Those drugs will be given over 5 days. Remdesivir now used early, approved to be used early. You're basically giving air support for the infantry. You're giving the ability to reduce viral replication, to allow the immune system to take over and do its thing. And that, in the case of COVID, we don't know yet about inducing resistance in that rapid a period of time. I don't think we're going to see that, but we do know that variants can emerge that are no longer responsive to, say, the Lilly and the Regeneron monoclonals in the case of Omicron, whereas Delta variant was quite responsive to that. And so we have to kind of keep up with things. But again, lessons learned about drug development, about drug use for antiviral therapy coming from the HIV world. And then finally, this notion of viral dynamics. This study was done as a team, in this case, bringing in a very young guy who was the Einstein professor of mathematics at Princeton, Martin Novak. And Martin basically took a single curve of viral decay that we could show with, in this case, it was indinavir, and came up with the notion that there are 1 to 10 billion virions produced a day with HIV, 1 to 10 billion. And that's true for a lot of viral infections, including SARS-CoV-2. So there's a lot of opportunity to knock that viral replication down without a viral therapy and give, as I said earlier, air support for the infantry. I think maybe most important from my experience in HIV was what I learned from patients. And this is a patient of mine from the late 80s named Michael Tipton. He was a ballet dancer, as you can see, quite talented. This picture was taken about 14 months after he was on a ventilator for 6 weeks with pneumocystis pneumonia. A very talented guy, danced in New York for the American Ballet Theater Company, and then got sick and was in Birmingham for several years and passed away in around 1991, but contributed a lot. And some of the lessons I learned from him and a lot of my other patients are really essential. And that is how to face the fear of the unknown. At that time, patients there was no therapies to speak of. They knew that they had a virus that likely was going to kill them. They just didn't know how and when and in what form that they would get sick enough to die. So they had like a Damocles sword over their head all the time. And when I got sick with COVID in early March of 2020, it was very similar. I didn't know what was going to happen to me. There were no therapies, just like for my patients with HIV. And that gave me a lot of courage as I fought through it. We're much better off now, some 22 months after that time or so. But I learned that from patients. I also learned to go public with the story. So as I went through this, I was doing interviews and a lot of things to kind of humanize the epidemic and let people know that this is serious business and to take precautions. And finally, to participate in research. The very first day I was tested, In March 2020, I had them draw extra blood. Later in May, I went back and had plasma and leukapheresis so that my antibodies and my cells could be studied in the laboratory. And I didn't have the chance to participate in a clinical trial, but I guarantee you I would have been first in line. And those are the lessons that we learned from COVID, among many. I'm going to segue now to more directly about COVID. And so the summary of HIV and COVID is what Yogi Berra said. It's like deja vu all over again. And a lot of the things that we're suffering through with COVID were similar to what our patients and we suffered through in the late 70s, early 80s, and into the 90s with HIV. Start off with this picture. Those of you who've seen my talks before know I use this a lot. This is Pigpen from Peanuts. And if you just move that cloud up to his face, that's what it's like when somebody has COVID. And they're spewing virus off into the environment around them, usually at a sort of radius of 1 to 2 feet, maybe up to 3 feet. But if they're talking, it might go 4 feet and 5 feet. And if they're singing, it goes out about 9 or 10 feet. If they're screaming like they're going to be doing tonight in an indoor stadium in Indianapolis, it could go out even further. So to say with Omicron around, as you'll hear in a minute, that there's going to be a lot of people who are unwittingly infected at that game. There's going to be a lot of transmission, I think, at that event tonight. We know that masks work. You can think about Pigpen, and if you put a mask over Pigpen's face when he's infected, that will block the spread or the spewing of that virus into the world around them. It really works, but it works kind of both ways. This is an interesting study out of the MMWR. It was published this fall. It was about Maricopa and Pima counties in Arizona. And what they found was that those school systems that adopted masks early had about an 8.4% sort of total prevalence of infection in that time period. And if they adopted it late, it was 32.5%. So just watching it happen, then saying, oops, we made a mistake, let's implement a mask policy, big difference. And those who never implemented a mask policy with no masks at all, it was 59.2. And remember, this is during the Delta outbreak. Omicron is even worse. And I think it's a very important challenge for us to just remain cognizant, remain calm in the face of this adversity with Omicron. That yes, we're all tired of this, but it's not our fault that Omicron's back, but we do need to manage it. And we know how to manage it. We just have to have the courage to go through yet again another brief time where, especially during this spike of cases that we're going through, we protect ourselves and especially our students and those in kindergarten and below who are not able to be vaccinated. It's a big deal right now. And this is a slide that I was given by Suzanne Judd in the School of Public Health, but it's really coming from a website on the Georgia Tech. It's called Georgia Tech COVID COVID transmission calculator. And what I want you to pay attention to is that this is at a time when Alabama had 39 cases per 100,000. And to walk you through it, based on that incidence rate, if you have 10 people in the room, the probability that 1 out of the 10 people are infected with COVID at that moment in time is about 40%. If it's 25 people in the room, the probability that 1 of the 25 would be infected is about 72%. Similarly, 50 patients, 92%. If you have 100 people in a room, it's almost 100% that 1 out of that, 1 out of the 100 people will be infected. If you look in contrast to that moment in time, Vermont had 2.5 per 100,000 in this example. You'll notice that even with 100 people, the probability that 1 out of the 100 is less than 30%. Right now in Alabama, as of yesterday, we have about 200 cases per 100,000. Yes, 200 cases per 100,000. And when you look at that, the probability that 1 out of the 10 is infected at a moment in time is now approaching 90%. So the point is that when we're in the middle of a spike, getting together with any kind of group puts you at high risk for being around someone who's infected. And I can't quite do the math in my head. I don't know how many people are going to be at this ball game tonight, but I suspect it'll be on the order of 50,000. And as a homework assignment, you can do the quick math and figure out how many people out of the 50,000 are likely to be infected tonight at that moment in time. And it's probably well into the couple of thousands who are going to be infected at that moment, probably nobody wearing a mask or very few, and yelling like Pigpen. It's going to be a mess. I already described how Delta and other variants emerged. This is how fast it happened from May of 21 until roughly about July. It took over, and here's Omicron. Kind of this is Delta now continuing on in orange, going into November around Thanksgiving, first part of December, and then boom, it starts to appear even just a month ago. That's how rapidly this happens. And over the 2 to 3 weeks after, it's become the dominant species. And as we all know, this Omicron variant is roughly 2 to 3 times as transmissible. Fortunately, it looks like the vaccines hold, even though somebody will have a breakthrough, they're not getting terribly ill with it. Sore throat is the number one thing I'm hearing. It's pretty wicked for a lot of folks, but it lasts only about 3 or 4 days. Not so much, at least among unvaccinated people, having problems with horrible respiratory problems unless they're unvaccinated. I don't need to say a word about this image. This is from the New York Times. A lot of you use this. This is from even several days ago. And this is the United States, where we're probably well over 1 million cases a day. Why do I say that? Well, these are the reported cases. I have several relatives who've called me over the weekend saying, I'm just tested positive with a rapid test. I don't think those positive cases are being recorded. So we can almost double the number of reported cases, and that's probably what the reality is. And look at that, it's all just in the matter of a couple of weeks. This is something I've never seen in infectious diseases before. Not only is it happening endemically, it's happening all over the world. And that pandemic with this kind of transmission is just, to my knowledge, unprecedented. The one thing that gives us a little bit of hope is that at least this is Alabama, and here are the number of cases spiking here as well. The hospitalizations tend to be lagging behind a little bit more than what they did here. You'll notice that our relative hospitalizations were mostly tracking with the number of cases back in last August. And now it seems to be dragging in. Deaths don't seem to be at least as much of an issue, although that lags, as you know. So those deaths from COVID Omicron probably won't be seen until the first part of February or so. But I don't think it's going to be as bad, mostly because of vaccination, and partly because even though Omicron is much more transmissible, it does appear to be a little bit less virulent. Real quickly, just like we learned with HIV, viral load drives the infection. This is the first 6 days of infection here with SARS-CoV-2. Symptoms might develop here about a day or 2 or 3 after exposure. The virus has been there, it's revving up, it's replicating at high copy rate. It's been spewing out of the person for a couple days before they develop symptoms. The symptoms seem to develop earlier in somebody who's vaccinated. That makes sense because all symptoms, I'm exaggerating a little bit, but not much, all symptoms from infectious diseases are the immune system response to the infection. So that the fever and all the things, that's response to interferon or interleukins. The virus itself isn't a fever inducer except with a body that responds to it. So during these first 6 to 7 days, there's an innate immune response, think interferon. and it kicks in about day 4 or 5, or peaks out about day 4 or 5. And it's a remarkably effective antiviral agent, and it drives down the virus. If we catch this early, we can abort a lot of that viral replication and therefore shorten the duration and reduce the severity of illness. And we do that in people by getting them rapidly into monoclonal antibody clinic or starting them on antiviral agents as soon as we can. Giving an antiviral agent out here at day 10 or 11 or 12, unless somebody's in the hospital, it's very unlikely to do any benefit. So we don't give outpatient therapy with antivirals that late. But it goes back to this principle that we learned in HIV and in other diseases, that treating early matters. And we see that with influenza, with Tamiflu. It's best if it's given in the first 24 hours after onset of symptoms. Same thing is true here with COVID. Later, there's an adaptive immune response. There's the antibodies. But remember, when people get a vaccine, this immune response is already primed, such that when that person encounters a virus out here again, those responses kick in almost immediately within a few hours, and antibody revs up and T cell responses. And that's how vaccines protect us. That's exactly what it does. People who've had prior infection also have this amnestic response. But it just like with the vaccine, it can wane over time as far as preventing breakthrough infection, probably due to the loss of antibodies circulating. We don't want antibodies produced 24/7 for the rest of our life from any infection, because I guess our bloodstream would become mud, wouldn't circulate very well if all we have was antibody flying around. So the way the body deals with it, it produces antibodies from the B cells once they're primed. As the infection starts to wane, the antibodies are told to stand down. The B cells, they don't produce as much, but they're ready to go again, just like NATO troops or our military, that if they sense, their intelligence tells them there's a problem, they gear up right away and start responding. So keeping that immune response primed is important, and that's why we're using boosters. Speaking of boosters and vaccines, this is something we do not have in HIV. We've been working on it since 1985, when Margaret Heckler, the Secretary of HHS, famously claimed that we would have an effective HIV vaccine in the next 2 years. Well, we're a long way from 1987, and we still don't have a vaccine. But the technology that's been developed, including the use of, or the concept of mRNA technology, was being bandied about for HIV, and it's going to be used in the future in the next couple of years for HIV vaccines. But as importantly, perhaps, is the notion of hybrid clinical trials to speed development. And that's exactly what was used. So instead of starting a phase 1 study, IRB, going through it, enrollment, analyzing results, announcing their results, designing a phase 2 study, launching it several months later, getting IRB. That's why clinical trials typically take so long in a traditional sense. The hybrid or accelerated thing, because once you start, you automatically have in the protocol that upon certain graduation features, you immediately go into the next phases without requiring development of a new protocol. And the IRB is kept abreast of this and approves it. What's also missed by the general public is the fact that we know these vaccines work. Here's the evidence from the Pfizer study. Day 0 is when the vaccine was given. Took about 12 to 14 days after the first dose for there to become a divergence. The blue line is the people in placebo, the red are the vaccine recipients. And you don't have to be a statistician to see there's a difference here, nor do you have to be a statistician to know that with this type of difference, up to 90%, the sample size to detect this difference is small. I mean, at most, you might need 200 people per arm, and you could have seen this with a high degree of confidence and a lot of power. But the studies didn't have 400 people or 1,000 people. They had 40,000 people. 40,000 people. You say, well, why'd they oversubscribe like that? Had nothing to do with efficacy. That's shown right away, probably about day 40. The Data Safety Monitoring Board would from efficacy alone, shut this down as being significantly different. The reason was safety. And the public has sort of missed that message. When you have 40,000 people, that's an enormously large study, and it was enrolled quickly, starting around the phase 3 portion, June of 2020, and it was completed enrollment by September, and the data were available by November. And as you well know, the vaccines were approved with early use authorization in December 2020. Again, lessons from, excuse me, HIV, and this time in clinical trial development, and highlighted, accented with Ebola during the 2015-2016 outbreak. We really refined how to do these types of hybrid clinical trials. The safety, and I think this is an important slide that shows that most of the side effects were local. There's a few systemic, but they're not as bad as you might see with the Shingrix vaccine, maybe a little bit more so with the flu vaccine. But remember, flu vaccine only works about 50%, and this one was working at 90%, which is quite remarkable. You say, well, what else does it do? Well, its benefits are really keeping people out of the hospital and keeping them from dying. And when people tell me, I'm not going to take the vaccine, like it's a yes, no question, it's not yes, no. It's asking the question, what's my risk of having something bad happen to me because I took a COVID vaccine? Versus what's my risk of getting COVID without having a vaccine? That's the risk benefit. And you can tell that getting COVID is a whole lot more risky than having a potential side effect from the COVID vaccine. And I'll get to at the end the notion of misinformation and problems there. We know that vaccines prevent against hospitalization and death. The hospitalizations are at least 6 to 7-fold higher, depends on when you're looking, but the protection against death is at least 12 to 15-fold higher. And there are very few things in medicine that are that effective. This is UAB Hospital a few days ago. Our number of cases are spiking, not so much because of the virulence of COVID, Omicron, but it is because of this is sheer numbers. And also among these vaccinated people, the roughly 46, they're incidentally infected, meaning they got admitted for something else. They tested positive, incidentally, as they got into the hospital, and they're not really sick too much with COVID. The beautiful thing is that when they come in early and they're not having COVID symptoms, we can give them remdesivir and some other things in the hospital, a great antiviral getting used early, and that's a helpful thing. But still, like we saw before, in the ICU, the vast majority are there with COVID, and especially those on ventilators, very few vaccinated people on ventilators. And most of those folks are, if they do have it from COVID, are there because they're immunocompromised, chemotherapy or immunotherapy that blocks their immune system. Then we know that protection and antibodies I've already described wanes, so that's why we're giving boosters, yet the T-cell immunity persists. And now we have approval for the vaccines in 5 to 11-year-olds, and that's been a real benefit, although it's not being taken advantage of like it needs to. It sort of twists my head when people are screaming, we need to get our kids back in school, we need to do it safely. They don't want to see kids wearing masks, and God forbid the kids get vaccinated. Well, those are the tools we have to get kids back in school safely. It doesn't add up. And it's because of misinformation that I'll finish the concept with. Before I wrap up, I want to tell you a little bit about this entity called Scenics, which has been applied to COVID. But when you think about it, this concept of Scenics is a database among 10 university medical centers in the United States who pool their clinical data. In essence, you take the clinical core of the CFAR from 1987-88 that we created for our CFAR here, and you pool it together with now 9 other clinical sites. But the difference in this is meant, its purpose sole purpose is to provide data and specimens to any investigator worldwide. Don't have to be at a Scenics site, although at UAB we are at a Scenics site by definition. But anybody from anywhere can submit a concept proposal. The sites are some of the leading HIV sites and by extension leading COVID sites in the United States, geographically dispersed, as you can see. And just in the last year, we added Vanderbilt and University of Miami, which broadens out not only our geographic diversity, but also the diversity of patient population. So at Fenway, it's mostly gay men, Caucasian gay men. In Miami, it's mostly Latinx, and UAB, and the South with UNC and UAB and Vanderbilt, a large majority of African American patients, San Diego, some Hispanic, and some and a fair number of gay men, just like in San Francisco. The overview, it's basically a dynamic, it's point of care. It's not an interval cohort that you recruit people into in numbers of 1,000 or 2. This is every person who attends at the clinic, who comes in for care, is offered participation. The acceptance rate is well into the mid 90%, so it's a large representative cohort taking place in a real world clinic. We've now enrolled well over 37,000 patients total and have about 16,000 plus in care. We have something called patient-reported outcomes, which are questionnaires that are given to patients about a myriad of things I'll show you, but the majority of our current patients have participated in that. And then we offer the opportunity for people, just like I did when I had COVID, but in this case with HIV, to donate blood that's stored in a repository for future use, and you've already seen the value of that. Roughly half the patients have participated. And then among those, we have stored genetic material based on genotypes and SNPs that are available for anyone to access. It's all under IRB approval. All the data and specimens are de-identified, and data sets are created for the investigator based on their needs from their study proposal. It's available to anyone at no cost. If you want to use the specimens, you have to pay for shipping, but otherwise it's available. 21% are outside of Scenics. I'd love to see that number start to approach 40 to 50%. That would show that we really are having the impact even beyond the Scenic sites. We have mentoring programs. So for those of you who are graduate students, even doctoral students or younger investigators, we set you up with a mentor from Scenics. And it can be somebody, in fact, ideally, it's somebody from a site other than where you are. So that gives you extra dimensions and extra dynamics. It also, the purpose is not only to help with design and implementation of a concept proposal, it assures that the concept proposal fits within the type of data that's in Scenics, so that there's reconciliation of the idea that the investigator wants with feasibility from the data. And well over half of our protocols are led by women. We have a rigorous data management core. The data, I'll let you look at that for a second, but it ranges just from not only diagnosis and laboratory and the patient-reported outcomes that I mentioned, but you could look at things like healthcare utilization. We've done several drug resistance, and more recently, as I mentioned earlier, we've done work with COVID and shown the differences between people with HIV and COVID versus non-HIV patients. The patient-reported outcomes are listed here. You look at the left side, you see the domain. On the right side, you'll see the actual instrument that we use to measure that. There's a few others that we can look at, like domestic violence has been measured, substance use, and we mentioned here, but also whether or not a person has suicidality. And that's been very helpful, because if they report things in a way that indicates suicidal thoughts, a beeper goes off in the clinic wherever they are, and a team comes in to evaluate them at that moment. That's a safety thing that we never anticipated would be part of the program, but it's really turned out to be critically important and has saved, I think, dozens of lives through having that assessment. It's in English, Spanish, and Amharic, and it takes less than 12 minutes to go through the pro. We now have it so you can do it on the phone on your way to clinic, hopefully not while you're driving, or when you get there before you go into the room. The specimens I've already alluded to, but there's a range of plasma, viably frozen PBMCs, snap frozen PBMCs that can be used for genetics, and in rare instances, saliva. Right now, this is our demographics. I think it's pretty representative of the epidemic nationwide. You can sort of peruse it there while it's up. And I think a critical part of Scenics, if you look at this, these are the people over the age of 70 that are in our cohort. The royal blue here is people in the age of 60. These are people 50 to 60. And you can see that well over half of our patients are over the age of 50. And that allows aging research to be done. It's high impact. Every year there's at least 3 to 4 dozen publications, but importantly, it also leads to extramural funding since our inception, well over 127 million in extramural grants, and these include R awards and K awards. And remarkably, from an NIH perspective, the cost of running this is $83 per patient per year, which is remarkably cost effective. I will mention one other thing. We can do intervention. So if you have a patient who has, say, substance use, and you want to do a protocol of intervention, could be behavioral intervention. We've done that for alcohol. You can implement that into the clinic without having to bring them back for a special clinic visit or pull them out of the flow. You can actually, while they're there on their clinic visit, implement an intervention so it becomes real world. If the thing works, then you know that it could be implemented in another clinic that isn't Scenics, and we can assess the cost of that and that type of thing. Finally, the website, I think what's important is this web URL over here, and Sudeep and others can provide that for you. But once you get there, there's ways to learn more about it, how to get started, and how to submit concept proposals. I'm going to finish with this. To me, one of the key similarities between the AIDS epidemic and COVID are activists. This is Larry Kramer. A lot of you know of Larry. He wrote the play The Normal Heart, which was about the AIDS epidemic, later revived on Broadway and won a Tony Award. But Larry was an activist who was there because of his anger about not enough being done to help patients with HIV. This is from 1988. And by partnering with the leadership in government and academia, the community and the academic world and the NIH world worked together to speed development of drugs, to spark research, and to make all the accomplishments that we've done over the last 30 years possible. When I contrast the energy and the direction and the vector of what the AIDS activists do or have done versus what I see in the COVID activist community, it's 180 degrees different. Because among COVID activists, they're on social media spreading incorrect information. The AIDS activists were accurate. A lot of them became pretty good at science over time. They respected science. They respected the truth. That's not true in the COVID activist community right now. They're on social media, Facebook, Instagram, Twitter, spewing lies and misinformation. And it's harming people. What the AIDS activists did was help people. The COVID activists are hurting people because it creates confusion, undermines trust in the system, but more importantly, assassinates the trusted voice, the voices of leadership that we need right now to get us through this. It's like assassinating a general in the middle of a war. And we can't afford that. And there doesn't seem to be any remorse. In fact, there's great pride among a lot of the COVID activists and the chaos that they're creating. And the only thing I can't quite get my head around is, what are they personally gaining from this? Is it monetary? Is it just satisfaction with messing up the system? I don't know. But it's making all of our jobs a whole lot harder, especially in the realm of public health. So it ain't over till it's over, Yogi Berra said. And maybe we'll be getting out of the COVID thing in the next year, at least in a big way. But we're not going to be out of the HIV challenge, partly because we tend to think of HIV as a bucket, as a group of patients, some of whom are known to be infected, some of whom are not, and we just attack and try to make things different and better. But what we have to remember is that every year, another group of young people come of age sexually, and they become the group that are newly at risk. And we have to keep in mind that this is constantly churning and evolving. And as we go into prevention methods, we have to find ways to communicate and implement strategies that we know work in terms of reducing transmission.